Hi there, my name is Dan Gray, and I gave this talk at Stellafane and at the Altaz workshop here in Portland, and it wasn't recorded, so Viktors is recording it. And without further ado, I'll put my coffee down. I did want to talk a little bit about the second law of thermodynamics. Can you give a shot of my desk? So this is proof of the second law of thermodynamics. It's hard for me to say that. All right, so without further ado, the topic of this talk is how to make your telescope more accurate, or something like that. And there's a little bit of history. And Robert Hooke, from Hooke's Law, and of course that's not a real picture of him, there isn't any, or a painting of him, in 1674 proposed a clock drive for a telescope. And he wrote a paper on it, and it was published. And a few people tried to make it, but they were all lame attempts, and nothing really worked until Joseph Fraunhofer, and you guys might know his name, because he invented the spectroscope. And also, he made the first successful clock drive for a telescope. So he made this telescope. It's called the Great Dorpat Refractor. Look it up. It's really a nice piece of history. There's a zoom in of the clock drive. You can see the weight right here. I should have a laser pointer. I don't have a laser pointer. Okay. And he had an actual governor on it. And this is actually, it's either in the museum rebuilt or somebody made a replica. Okay, so back in 1978, Sky and Telescope published a circuit for a variable frequency drive. And here it is. I got permission from them to publish this, and it's a schematic. I made this, and it worked. And I had push buttons, and I could look through a guide scope on my 8-inch refractor that looks like this, and I could keep something centered for a while. And so I began to take pictures. This is a picture that actually got published in Sky and Telescope magazine in, I guess it was 1980, no, 81. And it's, you can see the stars are a little bit squiggly, but you know, hey, I was really proud of it. And then a few more pictures of, you know, little surprises. I mean, you run, you wake up in the morning, you run as fast as you can, you drive into the 1 hour photo, and you get them developed, and you're so excited, and then you get results like this. Here's another one. This one was, I was guiding to, and I got a little squiggly lines there. This is Comet Hale-Bopp, I do believe. Well, how many of you have ever cut a 283 Chevy small block engine in half with a hacksaw? So this is now a V4 instead of a V8, and you can see that one wheel with a handle on it right here. That is how you adjust the altitude. The azimuth, you simply rotate the whole thing. I had a nice roller drive that had a lot of pressure on it. I knocked off the starter ring, and then I used one of the alignment pins for the bell housing to pivot the roller, and then I had a clock drive, a synchronous motor, and that turned a differential at the sidereal rate, and then I had a stepper motor that turned the outside of the planetary gear, and then I could slew with that. I used this computer here. It was available way back then, and I wrote a program that put out pulses on the printer port that made the stepper motors move. So I was really happy to look through the eyepiece of that, and there would be the galaxy or the star cluster right on the edge of the field of view. And this is all I could do. Then, Sky and Telescope published in '89 a basic program that you could give it 3 calibration points, and it would calculate your mount fabrication errors, what we call cone and hub now, and it would also do an alt-az telescope. It would do that transformation. So I converted that to C and wrote some software, and this is my telescope, my alt-az telescope that I made. And you can see Russ Genet, Howard Banich, Richard Berry, Mel Bartels, and me. I lost a little weight since then. And that was kind of a successful telescope, although I couldn't track very long because of one of the points later in the talk. Oh, right now. So what I did is I figured out that if you have a roller drive, and if there's a piece of dirt that lifts up that roller by 1/1000th of an inch, it's going to create 7 arc seconds of error. And that's what I determined was the problem with that mount. And that mount does not exist anymore. I think I might have some scrap pieces of it, but it's gone. Then, Russ Genet is one of the authors, and Mark Trueblood and Russ wrote these 2 books. I think one is an updated version of the other. And it turns out that the formulas used in those are still valid today. So this is a little fun I had. You can write a script with our software, and you can take an image of a star and make it right on your camera. Here's another one. I used a color camera for this with 3 filter wheels, so I could, you had to put your hat on the telescope, and then you had to, make a little spirograph here. Then I met Dave Rowe. This is the best picture I could find of it. This is a conference that we were at, and Dave Rowe is right here, and Russ Genet is right there, and there's a few other people that I know. And Dave, I met Dave and I showed him my Servo 1 controller because that's all we had, and he liked it very much, and he said, "Hey, I wrote some software for pointing a telescope. Do you want it?" I said, "Well, okay." So I converted his code from Visual Basic to C#. Now PointXP is migrated. It's a DLL that Dave Rowe lets us use by permission of Dave Rowe and Planewave, and courtesy of Planewave Instruments. So here's a screenshot of it. This is a mount model from my alt telescope mount. It's a Planewave CDK 12.5-inch telescope, and this is the one after I fixed the mechanical problem. And it was non-repeatable error, which we'll delve into a little bit later. And you can see here it's 5.2 arc seconds RMS, which is pretty darn good for a homemade telescope. It does have direct drive motors and absolute encoders on it. Here's another one. This is a Mike Rice's 24-inch from New Mexico skies. It's on an RCOS telescope. I think I might have a picture later on. And his RMS is 2.5 arc seconds. That's really good. This is a telescope mounted in South Africa. It's called Lesedi. I forget what it means. And here's the telescope model from that. 2.2 arc seconds, 8.6 arc seconds peak. Absolutely excellent. And it's an alt-az telescope. This is some of the model parameters that we have turned on. This is from the Lesedi telescope in South Africa. These terms here are for an alt-az telescope mainly. Okay, so here's another mount model from a customer in Ukraine. He's got 3.5 arc seconds. That's really good. And this one is really nice because all the ones that I've showed you previously they have on-axis, either absolute or incremental, high-resolution encoders. This one is from a 1-meter Bowler and Shipman's telescope in Chile, and a CTIO. And this is 2.4 arc seconds, and this is the worm gear. It's amazing how accurate, and it's a 1960s built telescope, and they knew how to make worm gears that were that accurate. This is at Oregon Star Party with my blue alt telescope. 7.8 arc seconds. I think that I had a little problem with the settling. So, okay, you may ask, how can you use Point XP? That's written by Dave Rowe. You can use our free software. All of our software is free. And it does include Point XP by Dave Rowe, and it's courtesy of Plane Wave Instruments. And it also has all-sky plate solving by Dave Rowe, which is really, really nice, and it's really fast, and it's accurate. Okay, so this is a screenshot of automation that will make a telescope pointing model. And this one was it's a virtual camera. You can see on the lower left that all those little stars. That software that I wrote that emulates where stars are from the star catalog. And so you can actually plate solve it. And I will do another demonstration of that later. And you also have to use one of our controllers. Okay, so the Servo 1 was first sold in about 2004, and it does brushed motors, and it's about 50 watts. Our second controller did about 100 watts, and it came out in about 2008. And then was our first brushless controller, and we call it the Force 1, and it does about 900 watts, and you can control conventional brushless motors that spin 5,000 RPMs, or you can control direct drive motors with it. And it will connect to absolute encoders by Renishaw, 26-bit or 32-bit, and they work extremely well. We'll talk about that later. And then we also have the Force 2, and it's about 5,000 watts. And it does brushless or direct drive, same as the Force 1. And then the final one that we just finished is a step direction controller, first sold this year. And it connects to our software, and it can control any industrial controller for any motor that has a step and direction input. So here's a picture of the Servo 1, Servo 2. You can see it has industrial terminal blocks, and you can connect an absolute encoder to this too with a little attachment. And it has high-speed 2 axes, like a scope encoder and a motor encoder for each axis. So there's 4 high-speed incremental encoder inputs. This is our Force 1, and it does brushed, brushless, or direct drive motors. Here's our Force 2. It does not have an enclosure, and probably never will, but it's a lot more powerful, and it has it's a little harder to configure, but it does position loop, velocity loop, current loop, all control loops inside it, and it's running I don't know, I forget, a 2 or 3 megahertz digital signal processor. It works really, really well. And this is our 1 megahertz step direction controller. It also doesn't have an enclosure, so you just have to mount it somewhere, but you can hook up ribbon cables and wire them to your equipment. Okay, so now I have a quote that nobody really knows how small an arc second is, and it's like a dime at a mile or something like that. It's very, very small. And we want to be under that for tracking a telescope. And so that's a hard problem. So when you're trying to make your telescope more accurate, you've got to have a goal in mind. And my goals over the years, I want to be able to take a 10-minute exposure and have negligible drift in images if you have, like, say, 1 arc second per pixel resolution. So this is a Cal Poly telescope, that's what it's called. And Cal Poly students made this, and we also fixed it, and we put on incremental, high resolution incremental encoders on it. And Richard Berry kind of took it over, and he did a lot of testing on it, and then now I'm getting it back again, so it will be here next week. I'm looking forward to it. Anyway, here it is at Richard Berry's place, and I don't know if you can see it, but there's this line that goes all over around here. That's all the sky that we could see from Richard Berry's place. That's his horizon limit. So I looked on Richard's website, and I found this talking about an image that we took. This is just one image, and he didn't do any processing other than some non-linear scaling. And here it is, and there's no visible drift of that for a 15-minute exposure. And so I will be testing this again, and we'll see how good we can do all over the sky next week. And if you want to go to this website, you can see Richard's blog on this telescope. It's very good. Okay, so we need to know, if we want to make your telescope more accurate, we need to know what time it is. And the easiest way to do that is with a time server on your local intranet. Wired one, not wireless. If you have wireless, you're going to get some jumps. We sell one. Go to our website, you can see it. And it uses a GPS, and it also uses a pulse per second, and it lines up your clock within about a millisecond. The accuracy of the clock inside the server is even more accurate than that, but we're just on the local intranet, it's usually about 1 or 2 peak, 1 RMS, I'm guessing. So you got to realize that 66 milliseconds of time is equal to 1 arc second of right ascension error. Now that, if you're making a telescope model, then that's going to affect your model. If you're doing long exposure and your computer clock is drifting, it's going to affect that too. It's also useful for doing science images. It'll log the time of your exposures very accurately. So here's a log of my desktop computer clock. So I wasn't setting the clock, I was only logging the time difference. And you can see it starts out with a milliseconds of 3 at the top, and then about an hour later at the very bottom it's off by 54, almost 1 arc minute, almost 1 arc second. And so that's what the time server is for, and you'll be glad you got one. Okay, now the other thing you can do is you can make your own direct drive mount, or make your own direct drive motors, or you can just add high resolution encoders to your existing mount. So here's mine. This is one that we use to do the eclipse. This is at Oregon Star Party. This is a coil that we can sell, and we finally learned how to make coils. It was quite a long process. And I'm going to go ahead and play this video. So those are the airplane simulator pedals. It's a joystick, really. There's a little friction, but we're not really using it. It's mostly a pulley. So we have a couple of servo motors here. One is guiding the wire. You can see how it jumped. Now it just changed direction. And then every time it does a wrap with a winding, then it scoots it over to the next slot, if you will. We're epoxying it as we wrap it. This is Daniel. And this is our first coil for this project. We have to make 48. This is a torque motor. And you see it just keeps the wire taut. And then if you go look at the software, you can see what's going on here. Okay. Number of turns, we've done 109, 110. We have 300 total layers. Number of layers needed. That must be the number of turns. Is it still working okay?
Seems to be.
Okay, we did that. So this is a close-up of the blue alt-alt telescope. You might wonder why I like alt-alt telescopes, and the reason I like them is because an alt-az telescope has the zenith where you have to avoid, and they call it the Dobson hole sometimes. An equatorial telescope also has a place where you need to avoid, and that's the north celestial pole. This telescope mount also has a place you have to avoid, but it's on the horizon, which you never look at anyway. So that's the biggest advantage of an alt telescope. So you can see the magnets. We use pie-shaped magnets on this one, and you can also see the encoder ring there, and the encoder. And this is a one where we've wired all the, this one's ready to go. There's the magnets. And if you do decide to make your own direct drive motors, we can help you figure out how to wire them. This is a series parallel setup, and this is a series winding setup. You would need more voltage if you had the same amount of resistance. Okay, so now we're going to talk about encoders, on-axis encoders. On-axis encoders covers a multitude of sins, and what I mean by that is if you have a worm gear and a worm, it can get rid of all your periodic error, even your backlash. You don't want that anyway, but it'll still be accurate, and all kinds of other things. But you need to be paying attention and doing them right. You want at least 10 ticks per arc second for a resolution for your Renaissance encoders, and the ones we like to use the most are 26 bits in absolute encoders, and they have about over 50 ticks per arc second, so 67 million for a full circle. So you won't have to guide if you do this. If you put on-axis encoders on your mount, you will not have to guide, as long as you don't have any other errors like non-repeatable errors. We'll talk about that in a little bit. There's two ways to use on-axis encoders. One is they are the motor encoder. If they're the motor encoder, then that means you have a direct drive telescope. That's the only way to have that happen. Or you can use a cascade mode. So now you have conventional motors on your mount, and the software looks at both encoders, and it says, okay, here's our Bible encoder is an on-axis encoder. And we move the motor until there's zero or close to zero error on the scope encoder. And that's what it says right there. Okay, so here's an example. This is a RCOS telescope. It's a 24-inch telescope in New Mexico skies. And you can see that encoder ring and reed head on the fork. So these have conventional brushless motors and absolute encoders on each axis. And this is the model that I showed you previously. Here it is again. Okay, so now you can install on an existing telescope that might be too big to install an encoder ring on, so you have to do a partial ring. And here's how we did it. So it looks like this would be one for each axis, but no, this is just for one axis. We mounted these four at 90-degree angle to each other, and we put them on the lathe and turned it. And we pinned it with dowel pins. And then we installed them on the telescope. You can see the right ascension axis. This is a 32-inch, I think, at 3 College Observatory in North Carolina. Here's another view. You can see the absolute encoder down there, the lower right of that. You can see we put tape on this, the encoder, absolute encoder tape. This is the declination axis. And here's a close-up of that. You can see the encoder tape that we stuck on the ring that we made. Okay, so now we're going to talk about bearing slop. And some of the stuff that I'm going to be talking about is stuff that I learned the hard way. And bearing slop is one of them that I learned the hard way. And it turns out, so if we have left to right bearing slop in this picture, then there's not much happens, everything's fine. But if we have bearing slop up and down in this picture with the reed head on the right, then a teeny tiny bit of bearing slop will create a large amount of error. So it turns out that as an example, if you have a 20 millimeter, 200 millimeter rings, about 8-inch ring, and if it moves 1/10 of a thousandth of an inch in the y-axis from this picture, it's going to create about 5 arc seconds of encoder error. And I found this out the hard way, believe it or not. So one solution is to add a second encoder on the 180 degrees out. Then if that bearing slop goes up and down, it will cancel. We do have an option for our force 1, and we're soon going to have one for the force 2 for 2 axis, 2 encoders per axis. Okay, so now we have to try to figure out how to mount the reed head to minimize bearing slop. So you have to think about gravity, and you have to think, we don't want it to move left or right if there's bearing slop. We want that to not change. So on a gem mount, you want it at the bottom if it's at the south bearing. Excuse me, if it's at the north bearing. If it's at the south bearing, assuming that the telescope weighs more than the mount, then you would want it at the top. Declination toward the south, and north if you're in the southern hemisphere. Fork mount is about the same. Altaz is really easy. Azimuth, you put it anywhere you want. Altitude, you put it at the bottom. Alt-out mount, like the ones that I like, on the primary axis you put it at the bottom. On the secondary axis you put it at the bottom when pointed east or west. Okay, so here's what's nice about these Renishaw encoders. This is a typical chart that you get when you buy a ring, and it tells how accurate the ring is. And you notice how nice and slow the error is. There's a little jump over on the right-hand side of that, and maybe you would be saying, why did my exposure drift in this? And it might be because you're right there. And point XP doesn't do that many terms. Okay, slow errors, though, by and large they're slow. That means it's easy for point XP to correct for the inaccuracies. The other thing you want to think about when you're mounting your absolute encoders, incremental encoders, it doesn't matter, but absolute encoders, you want to put the 0 point of the encoder where it's never going to cross, or where it's minimized going to cross. So, and this is where the 0 point is on the Renishaw encoder. You can see the writing, and it's by that hole. That's where it is. So here's the reason. So let's suppose we're putting out degrees and you're nearing the high end. So it's 357, 358, 359, 0. No, our software says 360, 361, 362. That makes it, not have to jump around and go the other way and stuff. So, or if you're like down at the bottom end, you go minus, or 3, 2, 1, 0, minus 1, minus 2, minus 3. The encoder itself spits out 3, 2, 1, 0, 359, 358, but we make it be minus 1, minus 2, minus 3. But the problem with that is if you're at 362, for instance, and then you power down, next time you power up, it's going to think it's 2. And so it could try to do a full wrap around or something. So you just want to locate those 0 points where you don't normally cross. Okay, so let's see if I back up. Because of this, it's important to locate the 0 point for the absolute encoders at the most appropriate position where the axis is unlikely to cross. For gem mounts, right ascension, you put it where the counterweight is clear up, pointed at your latitude in the south meridian. Declination, you want the scope pointed due south, so at the dirt, point at the dirt. Or due north if you're in the southern hemisphere. The fork mounts, right ascension, scope pointed at the northern meridian until the north pole, under the north pole. and then the southern meridian is, you go under the southern pole if you're down south. Declination scope pointed past north by 90 degrees, past the south pole by 90 degrees if in southern hemisphere. For azimuth, due north, or if you're in the southern hemisphere, due south. And the altitude over the zenith by 90 degrees, zenith if you're from England. For alt mounts, it's a little more complicated. The primary axis point to the zenith. Now move the primary axis until the scope is pointed at the nadir, straight down. Secondary axis do the same thing, point to the zenith. Now move the secondary axis until the scope is pointed at the nadir, straight down. That's where you want your transition point to be. This will keep the encoder from waking up at 358 degrees if it went to sleep at -2 degrees. All right, so I want to talk a little more about the cascade mode. That's a term from the control loop industry where I worked for a lot of years on ships, and we did control loops, and sometimes there would be a cascade control loop. When in cascade mode, the software drives the motors to the position where there is zero position error on the high resolution on-axis encoder. If you're using the cascade motor, or if you have a direct drive motor, you can have a nearly perfect telescope. I say nearly because there's no such thing as a perfect telescope mount. But it's so good that you don't have to guide, everything is always centered. It's just really a nice feature to have. Backlash is not good. It can create an oscillation, so you need to spring load your worms. Or if you have a roller drive, that's usually a sign of no backlash. So, positive feedback. Now, positive feedback is, oh, Dan, you're giving such a good talk. That's not the kind of positive feedback I'm talking about. I'm talking about the positive feedback where in a control loop situation. So we're back to this, and this is when I figured this out about the positive feedback. Mike Rice's telescope, we were trying to use a cascade mode, and the declination was going back and forth over a 5-second period. And I could not figure it out. I thought it was software, and I'm going through the code and can't figure anything out. And so I went to bed finally at 2 in the morning or 4 in the morning, and I woke up and I got to thinking about it. I said, I wonder if there's positive feedback. And so I did a little test. I put it in blinking mode. All you sci-techers know what that is, but basically I just make the motor so it's freely to turn by hand. And I started turning the motor clockwise while I was watching the raw encoder ticks on the software for both the scope encoder and the motor encoder. And as I'm turning the motor clockwise, the numbers on the motor are going up, and the numbers on the scope encoder are also going up. Okay, that's all good and well. Now I stopped, and now I turn the motor by hand the other way. And as I'm turning it the other way, the motor encoders go down, just like it should. But the scope encoders went up, and if you did the math, it was about 5 arc seconds. It went up about 5 arc seconds, and then turned around and started going down. So that's positive feedback. Now here's what I figured out the problem was. It was a friction of the worm on the worm gear, and it was using the worm the worm gear as a lever, and it was moving the whole telescope 1/10 of a thousandth of an inch. Remember I said a 200 millimeter ring is about 5 arc seconds? And so you see those two holes at the bottom of the fork on the sort of the lower left? That's where the encoder read head used to be. And I told Mike, I said, you know what, I think I figured it out. We just have to move the encoder read head over by 90 degrees. And he like, no, that can't be. And I explained to him, and finally he said, okay, go ahead. So I did it, completely solved the problem. So that's called positive feedback. We don't like that. Okay, so now we're going to talk about non-repeatable errors. Now this is another thing that I learned the hard way on my own telescope mount. And the quote that I like to quote is, if you tell a lie to point XP, point XP is going to lie back, and sometimes it'll tell you a worse lie back than you told it. So we do not like non-repeatable errors. An example of that is backlash. Another example of that is mirror flop. Well, I think I have a list of here. Mirror flop. So if your mirror cell has a little slop in it, flexure is okay as long as it's repeatable. But if it's slop and it suddenly shifts, that's not going to be good. Same can happen on your secondary mirror or tertiary if you have one of those. Focuser shift is another real common on some of these Schmidt telescopes. Backlash. Bearing slop is what we've already talked about. Okay, so here's how I found my problem on my alt-alt telescope in our observatory. I used a geosynchronous satellite, and the reason I pick a geosynchronous satellite is it's extremely likely that it's going to stay the same altitude and azimuth while you're doing your test. And so that you can assure that your encoders, I have on-axis absolute encoders on that mount, and I know that the telescope is in exactly the same place by the encoder reading. So if the images have the stars in a different point, then we know there's some non-repeatable error. Okay. Using a geosat, okay, I just said that. And now here's my setup. You can see the 12.5-inch plane wave, and you can see it's an alt-alt telescope mount, and it's got direct drive motors. Okay, so what we do is we center the geosatellite, and then we move all the way the primary axis, or whatever telescope you have. Primary would be the azimuth or the right ascension, or in the case of an alt-alt telescope, you just call it the primary axis. So you move as far as possible to the west, and then you return to the satellite, take an image, and name it appropriately. Now you move as far as possible to the east, and then you return to the satellite and take another image. You can do this with a star if you can't find a satellite, but a satellite's better, a geosatellite. And then you do this, you repeat with the secondary axis. Now when I press this next space bar, you're going to see a movie. See the star in the middle? That's the satellite. And you can see how it's shifting. And then there's an image of them all the images. So that's the amount of non-position error I have. And then here's a zoom up of that. And it turns out that that's about 1.5 arc minutes on my primary axis, and about, well, the secondary axis is a lot better. And it turned out that I just needed to fix some, stiffen some part of my mount, and it was really easy to fix. So after that, now my mount model is about 5 arc seconds RMS. Here it is right here, 5 arc seconds for that alt-alt telescope in my our little observatory. And you can see here, this is a plate solved by Dave Rowe that I'm using the software. And you can see that the little circle, the little green circle, that's the star we're analyzing, and its arc seconds is 2 arc seconds, which is extremely good for here. I usually get a lot worse than that as far as, because of the seeing. Here's a zoom in on it, and you can see that I have 0.7 arc seconds per pixel. You can see that it's 2.2 arc seconds average RMS diameter, and you can't see any drift in it. And this is the final image of those 2 nights that I had really good seeing. You can see this on my website somewhere, I think, and you can zoom in on it, and the stars are nice little points. All 5-minute unguided exposures. Okay, do you have any questions? Oh, you can't ask them. You'll have to email me. Okay, that's it.